So hello everyone, today I'm gonna just continue talking about regression analysis. Last time we just talked about the most of the elements that form the essence of regression analysis, and we talked about only one assumption, which is the assumption of the normality of the distribution of the residuals, or also in the very rare example that I shared with you when we were talking about I think temperature and pressure. I showed you how we actually used skewness and kurtosis to check the normality, and there were no alarming signs until we combined our investigation with an examination of the visual of the residuals. As you can see here on this screen, we found out that the residuals, or we were able to uncover or detect a hidden pattern in the plot of the residuals in the temperature versus the that was the temperature versus the pressure versus the temperature. Yeah, so in this case, this indicates that probably the very linear line or model is not the bestest model that could predict the outcome of the target or of the dependent variable. And we need to note here that despite the fact that we checked for skewness and kurtosis for the normality assumption, we found out that there's no alarming signs, and the distribution of the residuals were within the normal limit. However, this is an indication of the importance of visual examination of the residuals. All right, then to solve this kind of problem, or it's actually not, I would like to say to improve on the model so that we can actually get a better model than this linear line, which we end up with a bit of a model that I call it a curvature model. So it is kind of like linear model, but it includes, as you can see here, this is the model mathematically. As you can see here, this point is not exactly on the line. This point is not exactly on the line, but it's close enough. In fact, this is really a very unique case study. But in any case, over here, I wanted to get your attention to the fact that this model even is linear. And we treat it as a linear in nature because it has an intercept over here. It has one variable, another variable. So this x term could be x1, considered as x1. X squared term could be an x2 term. However, we all understand that x2 and x are dependent on one another, or there is a certain correlation between them because this x2 is actually extracted from x1. Yeah. So later in this section, when we talk about multicollinearity, which is the correlation between independent variables, this could be a very, very unique and special case where we understand that the x squared here is just very dependent on the x, and these are independent variables. So how could one variable be dependent on the other? Because it's extracted from it, and there's ways to solve this kind of problems. But for now, guys, I just wanted you to see how we can study a little bit of a case study of a linear regression, which is a curvature model. With this curvature model, we added one extra term that is dependent or extracted from the original x term, which is the temperature, by actually squaring it. So over here, we basically squared the temperature to x squared right here, and then we run a regression analysis again. When we ran regression analysis, we were able to also examine the residuals plots. Residuals plots, there is a plot for each independent variable, right? There's a plot of residuals for each independent variable, and we can see here that now the residual plots indicates randomness. There's no hidden pattern. And of course, over here, guys, you can see that skewness and kurtosis in within the limits, so the normality assumption is all right. There are other assumptions to test for linear regression, and we were going to talk about it in due course. So last time I asked you to work on this assignment, which is running a linear regression for this set of data. All right, so over here, first thing first is to actually plot the data. So let's plot height. So I'm going to do it. Now we started at 3:09 p.m. Okay, let's see how long it's going to take me to do it. So this is in fact how we plot it. Over here, this is height. As you can see, this is height versus we don't still know, so we're going to add. Let's add age, because you know that age here is a significant variable. And of course, our data set starts from 18. So let's just start from 15, for example. So format this starting minimum from 15 months. So over here, we have height versus age. Let's do another graph where we have height versus siblings. So you will see now siblings as if it's categorical data. So, okay. Yeah, the best way to do it is to start all over again. So insert over here. All right, it did it for me. All right. So over here, this will be, we can remove it. So this unit, this is to be edited. Over here is going to be height versus number of siblings, and over here the x is actually the number of siblings. I just want to make sure that, okay, and then y is over here. You see, it looks a little bit like categorical variable, the number of siblings, because we have either no siblings, 1, 2, 3, 4, 5 in our data set, right? So over here, this is our height versus age. So it is so obvious that this is kind of like linear kind of correlation, or linear, yeah, there's kind of linear correlation. Perfect. Over here, it is very difficult to see the linear correlation or the R person coefficient, just a linear correlation. So over here, if we add a trend line, we can easily find a linear line here, and here's the display and display R. If you want to change the color of the line so that you can see it better, then how about you just put it in red? And here we go. Over here, let's add a trend line. I told you guys, technically you can add a line, but how good is a line? The goodness of fit is a different story, isn't it? So here, and here's the R. The R is very low. It is 0.2. So just to be consistent, let's follow the same format with a red color for the, not for the line, in fact, not, oh man. Okay. I just need to, okay. So here we go. You can see that over here, there could be a certain correlation, linear correlation, but it is not as strong compared to the age, right? So the goodness of fit here is kind of a bit questionable. All right. Let's see what happens if we run linear analysis. So we go to the data, we go to data analysis, and then we choose a regression from the list. The Y range is the height. You can decide, you could decide to include the label in there. Don't forget to check the labels. And over here, these guys are the independent variables. I would like to have the residuals and the residuals plots, and the output somewhere over here. So here's okay. All right. So this is the summary output. Let's take a look at the output. We start with the goodness of fit, right, guys? This is the first comment here, goodness of fit. So looking at the goodness of fit, guys, we examine two very important measures, the R squared, but I like to consider the adjusted, right? Because now we have a multiple linear regression. So adjusted R squared over here. Adjusted R squared is in fact high, considerably high. It is 0.9. So this means that this model, we could say that this model is able to explain 99% of the variation in the dependent variable, which is height. In height, we don't need to say in the height. All right, a standard error, we already know how to examine the standard error, guys. We just need to find the how many of these points actually the residuals over here, the rest of residuals, in fact lie in within two standard errors. So we take the absolute measure of the residuals and see and check if it's in within. So if it's less than two standard errors, in this case this is a very favorable situation, so we assign it to 1, else we assign it to 0, and then find out how many. So over here we just found out that standard error, we just found out that 100% of residuals lie within two standard errors. Okay. So what do we need to do next? After we investigate the goodness of fit, in fact, we are going to move on to the ANOVA, table. With the ANOVA table, the measure that we would like or we are more concerned of is I'm sorry, just I'm sorry. Okay, I'm sorry. So I'm with you guys. So guys, after the goodness of fit, we try to take a look at after we consider the adjusted R square and the standard error, make sure that our errors, about a minimum 95% of our residuals or errors should lie in within two standard errors. Then we move next to the ANOVA table and look at the significance. So over here, the threshold to refute the null hypothesis is 0.05. We talked about what is the null hypothesis here. The null hypothesis indicates that this model in totality, with everything in it, with all the independent variables, is not in fact useful. Now, before I move on to the next step, I would like to compare height and age, the R squared, for example, for height and age, because this is a relative measure. Do you remember, guys, when we talked about this as being a relative and this is being absolute? So in fact, guys, being relative is not always bad. Relative means I also can compare if this model with age and number of siblings is better than age alone. The first model that we've done together with age alone, in fact, R squared was 0.0 0.98, or the adjusted r squared, do we have the output somewhere here? We have the output here. The adjusted r squared was 0.98. Right now, the adjusted r squared here is 0.99. So yeah, there is a bit of an improvement when adding an extra variable, but not that much really, but there is a bit of an improvement. Okay, let's move next to the third table, which is this table, the table of the coefficients. The coefficients are only considered reasonable when the p-value yields them to be significant. So first one is the intercept. The intercept, we don't really care about the p-value of the intercept. We care about the p-value of the independent variables. So looking at the p-value of the independent variables, we find out that both of them is, in fact, not both of them. Over here, the first one, let's color that with red and comment on it with red. So this one, let's over here use the color red. H, which is the x1, is significant. Why? Because the coefficient is actually less than the threshold, which is 0.05, because there's e2 minus 10. This means that there is 9 zeros ahead of the 1. So the decimal point will shift 10 decimal places to the left, to my left. So over here, take a look at 0.057. This indicates that it is a little bit on the borders of being insignificant. So we could just say that this is probably an insignificant variable. Why? Because this reading is in fact not less than this no siblings, or number of siblings, sorry, is not significant because of the threshold. I don't like to, I told you earlier, guys, that I always focus on the threshold being less than 0.05. Some scholars take it a bit easier depending on their study and their field of study as well, and the study in particular, and they can accept less than or equal to 0.05, but this is not even equal to 0.05, guys. It's not even 0.050. It is 0.057. So in fact, it is not even less than or equal 0.05. So in this case, we will conclude that this variable is insignificant, and the model is and for you to have a model with all significant variables, you would probably just consider age for now. All right, so this is how we do it. And in fact, if you are doing a quiz and you are asked to get the best linear model, then your next step will be by dropping the number of siblings and getting the and investigating the linear model with age only. And this is what we've been doing earlier. Because we've done it earlier, I'm not going to ask you to do it now, but this is the end of the requirements for completing the question for a quiz or for an assignment. But for this assignment, it's okay if you don't say delete this and do the investigation again with only age, because I know that you already done that. So for this purpose, we just gonna stop here. But in the quiz, again, in the quiz, you really need to say that we're gonna delete this and start a new tab and take the data set, the height and age with no siblings, and start the investigation of a new model without the insignificant variable or variables. All right, guys, thank you so much. And this is the solution for the assignment.